Hello, Chemistry 11 Honors kids. I hope you folks are doing well and you're getting used to these sort of videos and the video conferencing with myself and your other teachers. Today, what I wanted to do was introduce a new topic to you, which is an extension of what you have learned back in grade 10. In grade 10, you learned about Dalton, Thomson, Rutherford, and a little bit of the Bohr model in terms of explaining the atom. Today, what I want to do is I want to go a little bit further, okay? So hopefully all of you have downloaded the homework or the worksheet that I sent you. If not, please pause the video and find the link or the file and please download it, okay? So I'm just going to share the screen right now. Here we go. All right. Now, back in grade 10, you folks learned this, that Niels Bohr had introduced the idea that electrons circled the nucleus in specific orbits called shells or energy level. Okay? And each energy level could hold a specific number of electrons, and the configuration of the outermost electrons, or called valence electrons, determine the characteristics of each element. Now, you folks remember this from last year, hopefully, is that you would have your nucleus of your protons and your neutrons. And what you would have is you would have your orbits. And you would start with a 2, 8, 8. And remember, these were the number of electrons. Okay. Now, you learned that last year. Some of you drew brilliant circles. I just drew brackets and put the numbers behind or underneath because I was just lazy. Now, using this model, remember, this model explained why different elements gave off different light patterns, unique from each other and white light. Now, you can read, what is the difference between white light and element light? But what I want to do is I want to focus on why is a line spectrum produced? Okay. Now, when an atom is excited means that it gains energy, whether in the form the energy comes from light, heat, whatever. The electrons gain energy and move to a higher level or shell. And in order to return to the lower energy levels, the electron must lose energy that it gained. And the type of energy, light or energy given off depends on how much the electron received initially. So if we were to have an electron here, so let's say we had an electron here at a lower level. This is where it is stable. It likes to be in an orbit closest to the nucleus. Now, when it gains energy, what happens is the electrons can be kicked off into here, a higher level, or even here, higher level. At this higher level, it is unstable. We call it excited. It doesn't like to be in this excited state. And so what happens is that it comes back down to this stable level. And depending on how far it has to come down, that determines the light that's given off. So I just want to show you a little simulation. So what we have here is an example of a hydrogen atom. We have one proton, one electron. This 1, 2, 3, 4, 5 are the potential orbits that the electron can go to. There's 7, 8, 9, 10, whatever, but we just focus on the first 5. Now, when we add the energy, what happens is the energy is absorbed, the electron goes to an excitation, a higher energy level. To come back down to a little bit more stable, it released, you notice, a red light. If we added more energy, what happens is that it jumps into a higher level. Let's say to level 5. It's excited, too high, it doesn't like it. It comes back down, and notice in this case, it's a blue light. So depending on how far the electron has to jump back down and what type of energy it is releasing, that determines the color of light. Now, what you can do is take a look at this YouTube video, and that will show you what I was talking about. Now, why do we use this? Is because it's basically the idea of how fireworks are produced, depending on what type of chemical they are mixed with. What you get is you get different light given off because the elements have a different electron configuration, and depending on how many electrons are being excited and coming back down, what you get is you get different colors of light. Now, depending on how far the light jumps and depending on what region of the ultraviolet of the radioactive, I don't know, the spectrum, all right, it all depends. There's something called the Lyman, Balmer, and Paschen series. It all measures the energy the light is given off depending on which region of the, I guess the magnetic spectrum? I don't know. So we can have the ultraviolet, the visible, or the infrared region. All right, and they're called the Lyman, Balmer, and Paschen series. Now, to calculate the energy that is given off, scientists use this formula. E is equal to negative 2.178 times 10 to the negative 18 joules times Z squared over N squared. Now, E is the energy. Z is the nuclear charge or the number of protons. And N is the particular orbit. Now, notice it's negative 2.178. And the negative sign is because the energy of the electron closer to the nucleus is less than if it was farther away. In other words, going back to this particular diagram, at energy level number 2, the electron is more stable, has less energy than if it was in energy level number 5. Remember, this was stable, this was excited. Now, for example, what is the energy given off by a lithium atom when it travels from n equals 3 to n equals 1? Now, when we talk about it, we're talking about the electron. Okay, so how would we approach this question? Well, we would calculate. So at n is equal to 1, we find the energy, which is E, is equal to negative 2.178 times 10 to the negative 18 joules. In this case, 3 squared over 1 squared. Now, why is it 3 squared? Is because lithium has Z is equal to 3. Why? Because lithium has 3 protons. And what you would do is you would calculate some sort of answer. Now, you do the exact same thing, but you have at n is equal to 3. So you have E, this is not working, is equal to negative 2.178 okay, E, here we go, times 10 to the negative 18. Oh, my pen is not working. Okay, negative 18. And then you have multiply it again by z squared over n squared. And in this case, it would be 3 over 3. Let me just get my pen working. Times 3 squared over 3 squared. We would get another answer. And what happens is depending on the difference. So what is the difference? And that would give us the energy. Okay. All right. Now that was the Bohr model. But just to let you know, everything that you learned back in grade 10 was a lie. It's actually not true. So today what we're going to do is we're going to move on and we're going to talk about the wave mechanical model. Now, today's model of the atom uses the assumption that, whoopsie, electrons travel in a wave-like pattern. Now, how did it begin? Well, the idea is how can an electron give off light? If an electron is traveling in a straight orbit, how can it give off a wavy light? So that was the interesting part. So light, like waves, can be bent. Like a prism, the different wavelengths, the different amount of diffraction. And so what you have is you have the wavelength times the frequency is equal to the speed of light. Now, Max Planck theorized that the energy, such as light, is emitted in discrete units called quanta and can be calculated by the formula E, which is the energy, is equal to the Planck's constant, okay, multiplied by the frequency of light. Now, be aware that these two equations are related. Okay, please be aware of that. Now, Albert Einstein, famous Albert Einstein, suggested that beams of light existed as a stream of small particles called photons. Therefore, light existed as both particles and waves. So again, his famous equation, E is equal to mc squared. Louis de Broglie suggested that light not only displayed particle-like characteristics, but small particles like electrons may at times display wave-like properties. It's called the particle-wave duality. So these were all theories, and these theories put together came up with this idea of the wave mechanical model. And so for him, for Louis de Broglie, m is equal to the mass is equal to h, which is Planck's constant, divided by the frequency and the wavelength. Now, Erwin Schrödinger and Werner Heisenberg rounded off the ideas of this particle-wave duality. Now, you won't need to know these individuals, but you just need to know how their formulas, how to use the formulas, as well as how did you go from the Bohr model to this wave mechanical model. Now, with this background theory, we talk about orbitals or shells instead of orbits like planets, but they have a shape. Now, you can take a look on page 295, 296, 297 in your textbook. And when you look at those pages, you will notice that you will see a shape like this, a spherical shape. You will see one shape that looks like this, which is like a dumbbell. and you will see a shape that looks something like this. Okay? And even shapes like this. Now, again, these are all mathematical probabilities of where to find the electrons. Okay? The shape of the math is the mathematical probability of where the electron would be approximately 95% of the time for that given orbital. Okay, so when we say the orbital is S, that means it's spherical. P means that it is dumbbell, and the dumbbell can exist in 3 different planes: px, py, and pz. If you take a look on page 296, you will notice the px, py, pz. So you could have 2 electrons in this x axis, you could have 2 electrons in the y-axis, and you can have 2 electrons in the z-axis. Now, so this is why we take a look. The P can hold 6 electrons maximum, okay? And if you take a look, the D, oh yeah, something's wrong with my pen. That's okay. Hope it's not running out of ink. Haha, get it? Oh yeah. Okay. Pause it for a second there. There we go. The D can hold 10. So the typical electron configuration would be this. You would have something like 2p3. So 2 would be the shell. Would be the shell. Okay. P would be the shape of the electrons. And the 3 here, this would be the number of electrons. So in this case, if I said 2p3, then what that means is in the second shell or second orbital or the second energy level, there are 3 electrons that are in the dumbbell shape. Excuse me. When determining the electron configuration or orbital diagram, one needs to follow a couple of rules. There's the Aufbau principle, which means completely fill the lowest orbitals first before going on to higher orbitals. Hund's rule, if there are more than one orbital at a particular level, one electron goes into each orbital before they double up. And the Pauli exclusion principle is when an orbital does accommodate 2 electrons, they must have opposite spins. Now, let me give you a couple of examples, and then I'll let you go on to it. Okay? So let's say, for example, let's say we had calcium. Calcium, what you have is you have 20 electrons. Okay? Now, so what do we do is if we start from this orbital diagram, okay? So I've given you this guideline to help you start out. So here would be the nucleus. So we have 20 electrons. We have to represent the 20 electrons in this particular orbital diagram. So I'm going to represent them by arrows. So I'm going to start at the one closest to the nucleus, which is the 1s. So I have 1 and 2. Now, notice the second one I put in the opposite direction. Why? because they have to have opposite spins. Okay? Then, so that's 2, and then 3, 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So all 20 electrons are filled in. So what we do is you just write it out. So we have 1s2. Okay, whoopsie. Okay. 2s2. We have 2p6, 3s2, 3p6, 4s2. So that is the electron configuration. All right, we can try another one. Let's do, I don't know. Let's see here. Let me see if I can find one off the periodic table. So let's do germanium. Okay, now germanium has 32 electrons. Okay, so again, we have to have 32 arrows. So we've done 20. So now we fill in here. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Notice I filled in the 3D before the 4P because according to the off-bow principle, I have to completely fill the lowest orbitals first before we fill the other ones. And 3D has lower energy than 4P. So it would be 1s2. Okay, so there's a lag on my computer. S2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p. Oh yeah. Ooh, 4p2. Oh, it looks like my computer's a little messed up. Okay. All right, ooh, we're back here. Okay, so that's the electron configuration. Let's see if this will work again. Okay, let me see. Oh, looks like I might have too many things going on here. And that's why. Okay, there we go. We're back in business. 4p2. Okay, I'm going to stop it right here. And I want to give you a chance to work on doing some of the homework. So on page 322, what I would like you to do is numbers 45, 49, and 51. And then page 323, I would like you to do numbers 67 and 69. All right, so try those out. And yeah, if you have any questions, hopefully we will connect in the next tutorial. All right, thank you. You folks have a good day. All right, and see you next time.